Hello and very welcome back to our channel, and we continue our discussion on cascading of multiplexers in digital logic design. That means we'll understand how to make a large size multiplexers using small size multiplexers. So here on your screen, we have an exercise today to make a 4:1 multiplexers using two is to one multiplexers. So we want to use 2:1 MUX in the quantity of 2 to make a large size of 4:1 multiplexers. So how we do that? So this is what we are going to see here. So first of all, have a look at this schematic. You have got two MUX, that is MUX A and MUX B. Each of them have 2:1 MUX size. That means they have got two input data lines and one single output data lines. So the two input data lines for MUX B, for example, are I0 and I1. For 2:1 MUX A, the two input data lines are I2 and I3. Remember, you can also switch. You can call this MUX as MUX B or MUX. I would say you can call this MUX A with the data lines I0 and I1, and you can have the data lines I2 and I3 here for the MUX B. So depends on how you want to design it. Now, uh, one thing that we want to understand for the definition of the multiplexer is 2 to the power n is to 1 MUX. So 2 to the power n would be the number of input data lines. So for the 2:1 MUX, we have got two input data lines. One is the single output data lines, and select lines are indicated by a small letter n. And the select lines for 2:1 MUX is n equal to 1. And that is why when you put this value of n equal to 1 in this particular equation, 2 raised to the power 1 is equal to 2. They are your input data lines, and that's what we have done and shown over here. These two are the input data lines, and since n equal to 1 is a single select line, and this is your single select lines indicated by letter S naught. Remember and note, this single select line for 2:1 MUX is common to both of these MUX, and this is how we want to design a 4:1 MUX. So how do we do that? So S naught, you can see that that is coming from here, and that is common to both of these MUX. The input data lines already told, and the single output data line for top MUX A is indicated by X, and for the MUX B, the output data line is indicated by letter Y. And finally, these two individual data lines, we are using a logical OR gate to have the final output data line, that is X or Y. That is the digital Boolean equation. So having said that, we have got extra pin that is called as enable pin, indicated by letter E. This enable pin is basically used to switch on the multiplexer chip. Depends on what logic you apply to it. So when it receives the logic 1, the multiplexer chip is enabled, or in other words, switched on. So for that, we are using another line. We call it as a select lines S1, and that goes directly to the MUX A, and to the MUX B, that line comes through this NOT gate, logical NOT or inverter gate. So this we have done to finally construct 4:1 MUX. So now the definition of the 4:1 MUX, again, we come back to this formula here. You have got 2 to the power 2, that is equal to 4 input data lines, and one output data lines, and this letter n, which is n equal to 2, n equal to 2 are your select lines, and that is how you will make 4:1 MUX. So let us now see how this particular circuit or schematic will work as a 4:1 MUX. So we can indicate that by means of the truth table. So let us examine how this truth table will work here. So 4:1 MUX, two select lines S0 and S0, one single output data lines. So since there are two select lines, you have got four possible combinations of input: 0, 0, 0, 1, 1, 0, and 1, 1. So when your S1 is equal to 0, so for the first two cases, S1 is equal to 0, your logic 0 through the inverter becomes logic 1. With the positive logic, this chip of MUX B is enabled. This chip turns on. However, this chip turns off because it receives 0 and it makes it turn off. So this is not in the picture. This is in the picture. That means when this MUX B is enabled, I0 and I1 are ready. I0 and I1 data is ready to be transferred to the final output data line. And whether I0 gets transferred to the Z or I1 gets transferred to the Z finally, or right here, we can simply say just to the Y, depends on what you receive here at the S0. So when S0 is equal to 0, let us say 0 applies and that goes here 0. This 0 goes here as well, but top multiplexer is not on, so it is not in the picture. So when S0 is equal to 0, you can see that I0 gets transferred to the Y, or in other words, we'll see finally you receive the I0 at the output. However, S1 is still 0 and S0 is 1. So S0 is 1, this 1 comes here, that makes I1 to be transferred to the Y and eventually to the Z. Remember, Z is X or Y. So it receives logical X data or logical Y data. Now, the final two combinations where S1 is 1, that enable pin receives 1, this chip is turned on, this chip is turned off, and we are talking about this chip, so I2 or I3 are ready to be transferred to the X and then to the Z. Depends on what you have at the S0. So for example, so when S1 is 1, depends on now S1 is 0, then I2 gets transferred to the Z. And when S0 is 1, I3 gets transferred to the Z. So this is basically truth table for 4:1 MUX, where you've got two select lines, one output data line, and four input data line. So this is how you have constructed 4:1 MUX using 2:1 MUX. Now, have a look at this architecture or this schematic. The assignment here is you got to create 8:1 MUX using two 4:1 MUX. So it is very similar to the previous slide. So here we see that you've got again two MUX A and B, but now they are each 4:1 MUX. As the definition says, you have got 2 to the power n to the 1 MUX, and 4, if it is a 4:1 MUX, that means it is 2 to the power 2:1 MUX. And that means 2 to the power 2 are equal to 4. They are your input data lines. 1 is your output data line. This is the one here. And this n is equal to 2 because 2 to the power 2. They are your select lines. Okay, so where are those select lines that we need to see here? So this S1 and S0 are your two select lines for 4:1 MUX. Now, what we have done, this along with S1 and S0, we have used another line, which we call as a select line. Together they make three select lines, because eventually we want to create 8 is to 1 MUX. So if we go by the definition here, 2 to the power n is to 1, and if it is 8 is to 1 MUX, then it will be 2 to the power 3 is to 1 MUX, where 2 to the power 3 equal to 8 would be your input lines for the 8 is to 1 MUX. 1 would be output line, and in this case n will be equal to 3 for the 8 is to 1 MUX. That's why we have got this special connections here. Now, what we see here, how this 8 is to 1 MUX will work. So 4 is to 1 MUX, again, you got 4 input data lines for MUX big, 4 input data lines from I0, I1, I2, I3, then I4, 5, 6, 7. Together they are making 8 input data lines from I0 to I7. Note that you can also switch I0 to I3 here and I4 to I7 here, depends on how you design it. And look at how S2 is getting connected. S2 goes directly to the enable pin of the chip, which is to turn on or turn off the MUX. And S2 goes to enable chip of the MUX B through a logical NOT gate or an inverter. And this is how it will work. This combined circuit will work as a 8 is to 1 MUX. So here, single output data line from MUX A, single output data line from MUX B, together they are making X or Y. So let us understand how this will work as a 8 is to 1 MUX. It's quite simple here to understand with the means of truth table. Because it is now 8 is to 1 MUX, the full architecture, it has to have 3 input select lines. Remember, there is a difference between select lines and the input data lines. So these are the select lines, S2, S1, S0, S2 representing most significant bit, S0 representing LSB, that is least significant bit in a digital logic. Z is the final output. So let us say when S2 is equal to 0, 0 goes here, that turns off the chip, it doesn't turn it on. However, this chip, through the 0, it becomes 1 here due to the inverter turning on the MUX B. When MUX B is on, it is ready to transfer the data lines at the input to the output Y and eventually to the Z. Now depends on whether it transmit data from I0, I1, I2 or I3, depends on what is the combination of the S1 and S0. So S1 becomes MSB here and LSB is S0. Obviously, this will be always be MSB for the 3 if you take the 3 together, and if you take the 2 together, this is going to be the MSB. Okay, so S2 here in the first case is 0, MUX B is enabled. Now depend on S1 as 0, they will have 4 combinations 0, 0, 0, 1, 1, 0, and 1, 1. Based on that, you get at the output I0, I1, I2, or I3, one at a time. That is the definition of the multiplexer, many into one. So which of the many gets connected to the output depends on the combination of the select lines. Finally, if you look at the final 4 rows, this is you make S2 equal to 1, enable receives logic 1, turning this chip on, this chip turns off. Again, when this is on, whether I4 gets transferred to the output or I5 or I6 or I7 depends on what is the combination of logic inputs for the select lines you have. So again, when this is 1, whether it is 0, 0, 0, 1, 1, 0, or 1, 1, you will receive at the output I4, I5, I6, or I7. So whether I0 to I7, they have logic 0 or 1 at their input lines, that data of logic 0 or logic 1 is available at the output. So this is how we've got created 8 is to 1 mux successfully using two 4 is to 1 mux. Remember, you can compare this module with our previous modules where we are using multiple multiplexers, but here we are using an logical OR gate and reducing this number of mux that will be used. Here in this exercise, we have used only 2 mux. It is also possible to you can use 3 MUX, but now we replaced 1 MUX with the OR gate. So think about that. Having said that, we can move to the next one. Here you can clearly note the difference. What we are doing here is we want to make here 16 is to 1 MUX using two 8 is to 1 MUX. So I have got two chips, MUX A, MUX B, each of them 8 is to 1 MUX. That means 8 input data lines for each of them, I0 to I7 here, and I8 to I15 here. Remember, I0 to I7 can be input data lines to MUX A and vice versa. So it depends on what logic and how you want to design it. Since it is 8 is to 1 MUX, that means 2 is to 3 is to 1 MUX. This is how is the definition of the multiplexers here, right? So since it is this multiplexer, look, the truth table has also come. We'll see in a moment how this will work. So 3 are my select lines here. Okay, and 2 raised to the power 3 equal to 8 are my input data lines. That's what. And finally, 1 is the, excuse me. And finally, 1 is the output data line. Okay, so having said that, what we see here, the three input select lines are S2, S1, S0. S2 representing most significant bit, S0 representing less significant bit. And one extra select line S3 I have used here because finally I want to make 16 is to 1 mux. That means 2 to the power 4 will be the 16 input data lines. The 4 here, which is n equal to 4, are my select lines required. That's why I have to use S3 extra. So this together will make 4 select lines for 16 is to 1 mux. Okay, all is in this formula. 2 to the power n is to 1 mux. That's how you want to understand. Having said that, we see that truth table is ready here. And once the truth table is ready, we see now how it will work. So first thing first, S3 is equal to logic 0. Logic 0 is on the S3. That means E equal to 0 here, turning this chip off. But S3 through the inverter becomes logic 1 at the enable pin, turning this chip on. When this chip is on, I not up to I7, any single input data line get connected to the output data line, eventually reaching to the Z. That depends on what is the three possible combination of these three input select lines. So here 2 to the power 3 will be 8 possible combinations. So you see here for the first 8 rows where S3 is 0, and for the S2, S1 and S0, you have got 8 possible input combinations of the select lines. Okay, so when they are combinations of the select lines, depends your I0, I2 or I3 or I4 or I5 or I6 or I7 gets connected to the output. On the contrary, when S3 is equal to 1, enable is equal to 1, this chip is turned on, this chip is turned off. When this is the case, final 8 rows, again you have 8 possible combinations of S2, S1 and S0. And again here I8, I9 or any one of them gets reached to the output. That's why Z is equal to logical X or Y. So either you have X or Y. and that makes your final 16:1. So 16:1 here, 16 input data lines together. This schematic represents 16:1 MUX. So together you have 16 input data lines, 4 select lines, and 1 single output data line. So this is how you can construct 16:1 MUX using two 8:1 MUX. How about you want to make 16:1 MUX using 8:1 MUX or 4:1 MUX? So think about that, how you will do that. Let us move to the final slide. Here to the left side, we have got wonderful pictures that we are making 16:1 multiplexer using only 4:1 marks. But remember here and notice we haven't used OR gate or logical gate. It is purely only 4:1 marks. So 4:1 marks, we need them in the quantity of 5. 1, 2, 3, 4, and 5. So we've got 5 chips of 4:1 marks. Together they are making 16:1 marks. So definition of 16:1 marks is 2 to the power 4 is equal to 16 input data lines. So I0 to I3, I4 to I7, I8 to I11, I12 to I15. So from I0 to I15, the number is 16 input data lines. 2 to the power 4 is equal to 16. So 4 here is your select lines. So you need 4 select lines. So where are those 4 select lines? So you see here S3, S2, S1, and S0. S3 representing the most significant bit, S0 representing the least significant bit. They become your 4 select lines together. But individually for 4:1 marks, again definition is 2 to the power 2 is equal to 4 input select lines. But 2 to the power 2 here, this 2 here are your select lines for 4:1 marks. So 4:1 marks has 2 select lines. S1 representing the MSB, S0 representing the LSB. So these two individual here. Similarly for this individual marks, 2 is to two select lines and 2 to the power 2, 4 input data lines. So S3 and S2 are its own select lines. Z is the final output. The outputs of these individual chips are this one. Let's say W, V, X, W, and Y, something like that, or just call them A, B, C, D. Okay, so these are the ones. So yeah, that's it. So now how this will work. So it depends on the, you have got 4 select lines, S3 to S0, make a truth table, just like in a previous slide. And with that, you can see that S3 and S2, S1 and S0, put all the possible combinations of input. For example, let us go to the previous slide, and if we look at this truth table, if we consider this truth table, and here we can easily see that there are 4 input select lines, 16 possible combinations, and finally your I0 to I15 gets connected to the output. So you have, that's an exercise for you how it will go. Okay, try that by making a truth table right over here. Okay, now let us have a look at the right side of this picture. So here we are making 13:1 multiplexer. That is your task, but we want to make that using 16:1 MUX in the quantity of 2 and one single 2:1 MUX. So this is how we'll make. So obviously 16:1 MUX, again as per the definition, we have 16 input data lines. 2 to the power 4 becomes 16. So 4 here are the select lines. So these are the select lines from S3 to S0. S3 being MSB, S naught being LSB. And note, these select lines are common to the MUX B and MUX A. So this is how we make the configuration. So once they are common here, so you got 4 select lines, input data lines for each of them are available, and one single output data line. Let's call them as X and Y. So this is the 16:1 MUX. Together, you have to make 32 input data lines. So together here from I0 to I31, there are 32 input data lines. But for 32, 2 to the power 5 is equal to 32 input data line. The number 5 here, n equal to 5, is the required select lines. So 4 select lines are already there, and you have got another select lines. Together, they are making 5 select lines. So this S4 is basically a select lines of this 2:1 MUX, which is a single select line. 2:1 MUX, obviously X and Y are its own input data line. 1 is its output data line, which is also the final output data line of 32:1 MUX. And this is how you can now see that the together in this dotted box, this architecture is making 32:1 MUX. How this will work is very simple. When S4 is equal to 0 or 1, that depends on X or Y gets connected to the output. And for X, whether I0 to I15, any one of them is available at the X depends on what is available as from S3 and S0. Okay, the 4 input select lines here. Similarly, for Y, I16 to I31, which of them gets connected here depends on the combination of the select lines. So make a truth table of 5 variable here that to verify the complete operation of 32:1 MUX. That is an exercise for you. The final exercise is for the practice, make a 32:1 MUX using only 8:1 MUX. So the hint here, just first count how many multiplexer of 8:1 MUX size you will need to finally make a 32:1 MUX. Okay, the hint would be whether it is 4 or 5, just based on what we have explained to you so far. Try to make that. Okay, so hope you found this module useful to understand how the cascading of the multiplexers in digital logic design works, how we can make large size multiplexers using smaller size multiplexers, and a logical OR gate. Sometimes we don't need a logical OR gate. We can only use a multiplexers, what we have seen in these figures right here. And we'll continue our discussion with that. So if you like this video, share with the others for wider reach. Stay tuned for more engaging content like this. And till then, wish you a happy learning.